What if I told you that one out of every three trading algorithms that look mathematically perfect on paper, right, are actually ticking time bombs?
I mean, it's a genuinely terrifying statistic,
It really is.
especially when you consider just how much faith we put into the numbers that our computers spit out at us.
Yeah, like total blind faith sometimes.
Right, because we have this profound desire for certainty. You want to test a strategy, you see a high return, and you just want to trust that the math is this ironclad guarantee of the future.
Exactly. But today, we are looking at the invisible math that hides all that catastrophic risk.
And well, how a breathtakingly simple computational trick can fix it.
Right. A trick that takes, what, about 10 lines of code?
About 10 lines, yeah. And maybe 2 seconds to run.
2 seconds to reveal that invisible cliff edge before you step over it. So welcome to the deep dive. We are really thrilled you are here with us because today's topic is going to completely change how you view risk, success, and the danger of relying on just a single version of events.
Yeah, and our roadmap for this conversation comes from a really rigorous, mathematically dense article by a researcher who goes by the name Sunat.
Right.
It's titled Monte Carlo Bootstrap: How to Get Confidence Intervals for a Backtest in 10 Lines of Code. And I should point out, this is not just some, casual weekend blog post.
No, far from it. I mean, this work grew into a full-fledged research paper.
Mm-hmm.
We were talking about a study anchored by, like, 6,000 controlled experiments.
Yeah, 6,000.
The author tested scenarios with exactly known truths, simulating all different types of market environments. Data that behaves perfectly randomly, data that has heavy dependencies, trade-level simulations, block simulations.
And the raw data and the code are all publicly available too, right, for anyone to scrutinize.
Exactly. It provides a framework that is just incredibly robust.
Yeah.
But before we get into the actual mechanics of that framework, I think we really need to understand the psychological trap here.
The trap that quantitative traders fall into.
Right? And really decision makers in any field. We need to look at the allure of the perfect backtest.
Oh, the perfect backtest. It's so seductive. Let's set up that scenario for you. Imagine you are a quantitative trader.
Okay, I'm a quant.
You've spent the last, 6 months huddled over your keyboard, building an automated trading bot.
Lots of late nights, lots of coffee.
Exactly. You've programmed the entry signals, you've optimized all the stop losses, you've fed it the last 5 years of historical stock market data.
Right.
And this is the moment of truth. You hit the run button to see how your bot would have performed if it had been trading real money over those 5 years.
I can feel the tension. So the progress bar fills up, the computer crunches all the data, and the final dashboard loads.
And the numbers look absolutely spectacular.
This is beautiful. You are looking at a final profit and loss to PnL, right, of plus 42%.
22%.
You're already mentally spending that money, let's be honest.
Oh, 100%. And it's not just the total profit either. The risk metrics look equally pristine. The backtest shows a Sharpe ratio of 1.8 and a maximum drawdown of just negative 12%.
Okay, let's actually pause on those terms for a second, just to make sure we're all on the same page.
Good idea.
So a maximum drawdown of 12% means that at its absolute lowest point, your account balance only dipped by 12% from its previous all-time high.
Right.
So you made 42% total, and the worst pain you ever felt along the way was just a temporary 12% dip.
Which is an incredibly comfortable ride. I mean, anyone would take that. And that comfort is reflected in that Sharpe ratio of 1.8.
Yeah, the Sharpe ratio, that's a term thrown around constantly in finance.
It is.
But a great way to intuitively think about it, I think, is as your profit per unit of roller coaster.
I love that phrasing. Profit per unit of roller coaster.
Right, because a high number like 1.8 means you are making fantastic returns on a very smooth, predictable train ride. Whereas a low number, say 0.4, means you might be making the exact same amount of money in the end, but you are getting violently thrown around, suffering massive drops and wild swings just to get there.
Precisely. So a 1.8 Sharpe ratio with a 12% max drawdown is a dream scenario. It looks flawless.
Total dream.
It basically tells you that your logic is sound, your risk is minimal, and your edge in the market is real.
So obviously you do what any rational human being looking at that math would do.
You launch it.
You connect the bot to your live brokerage account, you fund it with your actual hard-earned capital, and you launch it into production.
And 1 month later, you log into your brokerage account and you are down 28%.
Ouch.
Yeah.
Your maximum drawdown. The absolute worst case scenario that your pristine backtest promised would never, ever exceed 12% has just more than doubled.
It's a nightmare. Your beautiful upward trending equity curve is just in a free fall.
And you are bleeding capital every single day.
So the immediate instinct, right, is to look for an external culprit.
Always. Who's to blame?
Was there a bug in the code that only triggered in the live environment? Did the market undergo some massive, unprecedented structural shift the exact week you decided to turn the bot on?
But the source material makes a really striking claim here. It wasn't a bug in your Python script.
No.
And the market didn't suddenly conspire against you.
Yeah.
The flaw was entirely in the math.
Well, or rather, the flaw was in how you chose to interpret the mathematics of that initial historical backtest.
Right.
We really have to dismantle what we call the single point estimate.
The original sin of algorithmic trading.
It really is. When you run a historical backtest, you are running your strategy through one very specific, unchangeable sequence of market events.
Because the market behaved exactly one way from January 1st to December 31st.
Exactly. And the bot interacted with that specific timeline, yielding a single final PnL, a single drawdown number. It's just a single data point.
But relying on that single data point gives you a profoundly misleading picture of the actual risk profile of your strategy, doesn't it?
It does. The author of the paper uses an analogy that perfectly encapsulates the absurdity of this. Relying on one historical backtest to predict future performance is mathematically equivalent to taking a six-sided die, rolling it exactly once, watching it land on the number 4.
Okay, roll the 4.
And then confidently concluding, well, this die always lands on 4.
When you frame it like that, it sounds insane.
It is insane. No one would ever make a financial bet based on one roll of a die.
Right, but a trader looking at a 5-year backtest thinks they've done rigorous analysis. They don't see it as a single die roll at all. They see it as hundreds of individual trades.
I know, but the sequence of those hundreds of trades is just one realization of a massively complex random process. Let's look at the specific example cited in the research. They analyze a strategy that executed 491 trades over its historical backtest.
491 distinct moments where the bot bought and sold.
Right. Now, every single one of those 491 trades is effectively a random event drawn from a certain distribution of possible returns.
Meaning, sometimes the bot wins a little, sometimes it loses a little.
Exactly. Occasionally it captures a huge trend and wins big, and occasionally it gets chopped up and suffers a big loss.
I'm struggling with this a bit, though. Let me play the skeptic here for a second.
Please do.
If 2023 happened exactly the way it happened, and my bot made 491 specific trades based on the real, actual price of Apple or Tesla or whatever,
Yeah.
why do I care about viewing it as a random process?
It's a fair question.
Because I can't trade in a parallel universe. The historical order is the only one that actually matters because it is the only one that physically occurred.
Right, and that is the absolute most common mental hurdle traders face. You have to ask yourself what the fundamental purpose of a backtest actually is.
Okay.
Are we trying to accurately describe the past? Or are we trying to predict the future?
Well, obviously you want to know if the bot is going to make money tomorrow.
Right.
We already know what happened yesterday.
Exactly. We are evaluating the underlying system, not the historical timeline.
Ah, I see.
The historical run only shows us what the system demonstrated under one highly specific set of environmental conditions. It does not tell us the true underlying capability of the system, and it certainly doesn't tell us how much we can trust that performance going forward. The future will absolutely not be an exact chronological replay of the past.
Okay, so the sequence of wins and losses tomorrow will arrive in a completely different order than they did yesterday.
Precisely. Now imagine if you took those exact same 491 historical trades.
Okay.
You don't change the win rate. You don't alter the size of the wins or the losses. You have the exact same set of physical results. But you simply shuffle the order in which they occurred.
Like taking a deck of 491 cards, where each card has a dollar amount printed on it, some positive, some negative, and just totally shuffling the deck.
Yes. If you shuffle that deck and deal them out one by one, your final profit and loss at the very end of the sequence will be mathematically identical.
Because addition is commutative.
Right. The order doesn't change the final sum. You still made your 42% by the time you flick over that 491st card.
But the journey to get to that 42% could be completely violently different.
Radically different. What if, in your newly shuffled deck, by pure statistical chance, your 10 worst losing trades just happen to get dealt back-to-back right at the beginning of the sequence?
Oh, wow. Yeah. If I take 10 massive hits to my account balance right out of the gate, I might hit 0.
Exactly.
My account is wiped out before I ever get the chance to experience the winning cards that are just sitting there at the bottom of the deck.
That is the invisible cliff edge. The sequence dictates your maximum drawdown.
Wow.
The specific historical sequence that you backtested against might have luckily, spaced out your losing trades so your account had time to recover and compound.
But a different sequence of those exact same trades could create a drawdown so deep it triggers margin calls.
It ruins your psychology.
Right, and completely wipes out your capital.
Yeah.
So the historical backtest only showed you one lucky realization of that sequence.
So, relying on the historical timeline is essentially betting your life savings that the future will unfold in the exact same lucky, convenient order as the past.
And that is a bet that the market will eventually punish.
Always. We don't need a single point estimate. We need an interval. We need a way to mathematically state, based on the characteristics of this strategy, we can say with 95% probability that the maximum drawdown will be between X and Y.
We need to know what happens to our account if luck is absolutely not on our side.
Right.
But that creates a massive logistical nightmare, doesn't it?
Yeah.
If we agree that a single historical sequence is a flawed metric, how on earth do we simulate alternate histories?
What?
Because we can't just invent fake market data. If I just start hallucinating fake stock prices to test my bot against, the test is entirely meaningless.
But you don't need to invent fake data, and this brings us to the absolute elegance of the Monte Carlo Bootstrap.
Oh, this is the mechanism that absolutely blew my mind when reading the source material.
The Monte Carlo Bootstrap is a statistical resampling method. It was introduced by a brilliant statistician named Bradley Efron in 1979.
Wait, 1979. So we aren't talking about some bleeding-edge, impenetrable AI machine learning black box here.
No, not at all.
This concept has been around since the days of the Apple II.
It has, but Efron's conceptual leap was profound, and it requires modern computing power to truly leverage effectively. The idea is brilliant in its simplicity.
Okay, break it down for us.
If we have a robust data sample, like our actual historical record of 491 trade returns, we already possess a highly accurate representation of the strategy's true distribution.
So we don't need fake data.
Exactly. We can generate thousands of new, highly realistic alternative timelines by randomly selecting elements from our original dataset. But there is a crucial catch.
What's the catch?
The entire method hinges on one mathematical rule.
Right.
We must select them with replacement.
Let me see if I have this straight, because with replacement is really the phrase that pays here. Let's really play this out using that deck of cards analogy.
Okay, let's walk through the actual mechanics. You have an array in your computer's memory. Basically, a simple list containing the monetary return of every single one of your 491 historical trades.
Okay. Trade 1 made $10, trade 2 lost $5, and so on.
Right, so you have your deck of 491 cards.
Got it.
You tell the computer to randomly draw one value from that array to start building a brand new timeline. But because we are resampling with replacement, after the computer notes the value of that first draw, it puts that value back into the original pool before it draws the second time.
Okay, so if I manually did this, I would pull a card from the deck, write down lost $5 on a fresh piece of paper, and then crucially, I put that lost $5 card back into the deck, reshuffle the whole thing, and draw again.
Exactly. You repeat that drawing and replacing process 491 times to build a complete alternative history.
Which means, mathematically, if trade number 12 in my history was an absolutely agonizing, portfolio-crushing loss,
Yeah.
in my new alternative universe,
Yeah.
I might pull that terrible card twice. Or 3 times.
Or, if you get lucky, you might not pull it at all.
That's fascinating.
By resampling with replacement, you are building a completely new equity curve. It is a new sequence of trades that maintains the exact statistical DNA of your original strategy.
Because the cards are the same.
Right. It has the same overall probability of winning, the same distribution of massive gains and tiny losses, but the specific sequence and the frequency of those specific trades is dynamically altered.
Wow.
It creates a mathematically valid alternative scenario of what could have happened if the market had behaved just slightly differently.
It's effectively creating a multiverse for your trading strategy.
It really is. And we don't just visit one alternative universe. We automate this process. We tell the computer to repeat this resampling loop 10,000 times.
10,000 alternate realities. Now, the immediate thought that jumps to my mind is the computational cost of that. When you say we are generating 491 random draws, putting them back, shuffling, and doing that entire process 10,000 separate times, I mean, that sounds like a job for a supercomputer running overnight.
And that is the most incredible revelation in Stuno's paper. The author provides a complete working implementation in Python, and the entire operation takes roughly 10 lines of code.
Wait, what? Just 10 lines? What is the computer actually doing in those 10 lines that makes it so wildly efficient?
It leverages optimized mathematical libraries, specifically NumPy.
Ah, NumPy.
Yeah. Instead of writing slow manual loops like we described with the physical cards, the code uses a function essentially like numpy.random.choice.
Okay.
It tells the processor, here is an array of 491 numbers. Give me a new matrix that is 10,000 columns wide and 491 rows deep, filled by randomly picking from this array with replacement.
And because it's NumPy, it's fast.
Because modern CPU architecture is incredibly efficient at generating random numbers and managing arrays in memory, this massive matrix generation happens almost instantly.
How instantly? Like, what are we talking about here?
On a standard, off-the-shelf laptop, executing this 10,000 path simulation takes approximately 2 seconds.
2 seconds.
2 seconds.
10 lines of code. You go from having a massive invisible blind spot that could destroy your entire net worth to having 10,000 fully realized simulations of risk. The asymmetry of that effort versus the insight gained is just staggering.
It is arguably the highest return on computational investment in quantitative finance.
But that leaves us with a very practical problem, doesn't it?
What's that?
Well, we run this 2-second miracle, and suddenly our computer screen is vomiting a mountain of data. We don't have one final profit number anymore. We have 10,000 different PnLs. We have 10,000 different maximum drawdowns.
Right.
How does a human being actually extract something actionable from that massive pile of numbers?
This is where we shift from generation to analysis. We use percentiles to find what the source material calls the realistic worst case.
Okay, let's dive into the actual numbers from the research, because this is where the theoretical multiverse crashes into hard reality. We need to contrast that initial perfect backtest we talked about earlier with the reality revealed by the distribution.
Let's do it. Let's start with the profit and loss. Our initial single-point backtest promised us a return of plus 42%.
Right.
But when we take the 10,000 alternative realities generated by the Bootstrap, we organize them in a list from worst to best.
So the first percentile is the absolute nightmare reality where everything goes wrong.
Yes.
And the 99th percentile is the utopian reality where the bot just prints money.
Correct. The research suggests focusing our attention on 3 key markers. The 5th percentile, which represents the boundary of the worst 5% of outcomes.
Okay.
The 50th percentile, which is the median or middle of the pack outcome. And the 95th percentile, the boundary for the best 5% of outcomes.
So if our original dream backtest was plus 42%, what does the Bootstrap actually reveal?
The median outcome, the 50th percentile of all 10,000 runs, is plus 41.7%.
Okay, I take a deep breath. That is highly reassuring.
Yeah.
The middle-of-the-pack alternative reality is almost identical to our original backtest.
Yeah.
The baseline expectation hasn't really changed.
It hasn't. But we don't plan for the median. Look at the 5th percentile. In the bottom 5% of our alternate histories, the PnL drops all the way down to plus 18.3%.
Wow. That's a massive haircut. You are less than half as profitable as you thought you were going to be in a realistic worst-case scenario.
And it gets significantly more alarming when we examine the maximum drawdown. Remember, the single backtest promised a very manageable negative 12% drawdown.
Which we built our entire risk model around.
Exactly. But the Bootstrap reveals that while the median drawdown is negative 12.8%, in the 5% worst scenarios, the drawdown plunges to negative 23.4%.
Negative 23.4%.
Yeah.
That is nearly double the risk the backtest claimed. We really need to pause and think about the human element of that number.
It's intense.
If you planned your position sizing, your leverage, and your emotional fortitude around a 12% max pain threshold, hitting a 23% drop in live trading is devastating. That's a quarter of your wealth evaporating.
It is.
That is the kind of drawdown that makes traders panic, manually override their bots, and lock in catastrophic losses at the exact wrong time.
It causes psychological ruin just as often as financial ruin. So true.
And finally, let's look at the Sharpe ratio. The initial backtest showed that stellar 1.8. But the Bootstrap exposes that the lower bound, the 5th percentile, is only 1.12.
Which puts it in a completely different tier of strategy. A 1.8 Sharpe is a money printing machine that you can scale up with massive leverage.
Yes.
A 1.12 Sharpe is, I mean, it's fine, it's profitable, but you are getting thrown around a lot more for every dollar you make. It's much closer to the edge of not being worth the underlying risk.
It completely changes how you size your bets.
But let me argue on behalf of the greedy trader for a second here.
Go for it.
We are spending all this time staring into the abyss of the 5th percentile. Why shouldn't I focus on the 95th percentile? Because according to the data in the paper, the 95th percentile outcome is a PnL of plus 72.1%. Isn't it just as mathematically likely that I land in the amazing 72% reality as it is I land in the measly 18% reality? Mathematically, yes, you're right. The 95th and 5th percentiles are equidistant in terms of probability from the median. But your question touches on a fundamental philosophy of risk management and survival in chaotic systems.
Okay, lay the philosophy on me.
In finance, in aviation, in structural engineering, you do not plan for the best-case scenario. You plan for survival.
Right.
The 5th percentile represents your realistic worst case. If your strategy breaks down, if it stops being profitable, or the drawdown becomes intolerable at the 5th percentile, then launching it into production isn't an investment, it is a gamble.
Because if you happen to hit that 5th percentile reality in live trading and your account isn't capitalized to survive a 23% drawdown, you blow up.
Yeah.
The account goes to zero. Game over. You do not get to keep playing to see if the 95th percentile shows up next year.
Exactly. You have to survive the short term to achieve the long term. As the old market adage goes, in order to succeed, you must first survive.
Survive first.
The 5th percentile tells you exactly what kind of pain you need to be prepared to endure. If you cannot stomach the 5th percentile numbers, you cannot trade the strategy no matter how good the 95th percentile looks.
That is a harsh but absolutely necessary reality check.
It is.
Now, staring at a table of percentiles is great for the analytical mind, but human beings are visual creatures. We process shapes, patterns, and threats much faster than we process columns of raw numbers in an Excel spreadsheet.
Totally.
How do we actually see this risk?
This is where the visual tools associated with the Monte Carlo Bootstrap become incredibly powerful. The source material highlights two specific, striking visualizations: the fan chart and the probability of ruin chart.
We'll talk about the fan chart first because the imagery here is just brilliant. Imagine a standard chart showing an account balance growing over time.
Just a single line.
Right, a single line starting at the bottom left of your screen and hopefully wiggling its way to the top right.
That single line is your standard backtest.
Right. Now, instead of one line, imagine 10,000 lines, all starting from that exact same 0 point on the bottom left.
Right.
As they move to the right, representing time and trades unfolding, they begin to spread out based on their different alternate histories. They fan outward, creating a massive spray of color on the screen. The top lines soar into massive profit, the bottom lines drag down into the mud. It literally looks like a fan opening up.
And interpreting that fan chart is beautifully intuitive. The shape of the fan tells you immediately, at a glance, everything you need to know about the internal stability of your strategy.
What does it mean if the fan is very narrow?
If the fan is narrow, it means all 10,000 alternate realities are tightly grouped together. That means your strategy is highly robust.
Okay.
It means the final outcome does not heavily depend on the random luck of the trade sequencing. Whether you happen to get your losing trades early in the year or late in the year, the overall curve remains fundamentally intact.
But what if the fan is wide? What if it looks like a shotgun blast covering the entire screen with lines going everywhere?
A wide fan means your strategy is dangerously vulnerable to luck. It implies that your profit is heavily dependent on a few specific trades occurring in a specific order.
Wow.
A slight change in the sequence, a slight variation in the market's timing could mean the difference between a massive profit and a devastating loss. A wide fan is a glaring red flag that your algorithm is unstable.
That visual alone is worth learning the 10 lines of code. But the text shifts to an even darker visualization. The probability of ruin chart.
Yes. The fan chart shows you the spread of possible outcomes. But the bootstrap allows us to answer an even more critical and, frankly, terrifying question.
What's that?
What is the exact mathematical probability that this strategy will lose a catastrophic percentage of its capital?
The ultimate worst-case scenario, hitting zero.
Right. In the ruin chart, you establish a threshold. Let's say losing 50% of your initial account balance. For most traders, a 50% loss is unrecoverable. That is your ruin line.
Makes sense.
The chart then visualizes all 10,000 paths again, but this time it color codes them based on survival. The source material describes a chart where the paths that survive, that stay above that 50% threshold, are colored a bright, reassuring cyan, curving upward.
And the paths that hit that ruin threshold.
They are colored blood red, and you can visually see them dropping, one by one, crossing below that invisible zero-equity cliff edge.
It's quite literally a cliff of ruin.
It is. And here is the most vital insight about these visualizations. Seeing these ruin metrics, seeing this visual cliff edge, is mathematically impossible to achieve from a single backtest run.
Because a single backtest only has one path. It is entirely binary. It either hits ruin or it doesn't.
Exactly. A single backtest that successfully navigated the historical data and didn't hit ruin tells you absolutely nothing about how close you came to the edge. You might have missed total ruin by a millimeter.
It's terrifying.
Only the Bootstrap, by simulating those 10,000 alternate sequences, reveals the invisible cliff edge you might be standing right next to. It shows you that in 4% of alternate realities, you fell off the cliff.
That is incredibly sobering. It's like finding out you've been confidently walking a tightrope across a canyon and you thought you were on a wide bridge because you were blindfolded.
That's a perfect analogy.
So this Monte Carlo Bootstrap sounds like a flawless, omniscient crystal ball. It takes 2 seconds, 10 lines of code, gives us deep percentiles, intuitive fan charts, and reveals the invisible cliff of ruin. But I know enough about statistics to know that no mathematical model is perfect.
Oh, absolutely not.
Every model has blind spots. When does this 2-second miracle actually fail us?
That is the perfect question to ask because understanding the limitations of a statistical tool is just as important as understanding its power. Misusing a tool can be more dangerous than not using one at all. We need to focus on when the classical Bootstrap fails and, crucially, how the research tells us to fix it.
Okay, the text outlines a few critical limitations. Let's start with the first one, which sounds a bit dense. Autocorrelation.
Right. The classical Bootstrap, the basic version we've been describing, where you just toss all 491 independent trades into a hat and pull them out randomly, makes one massive foundational assumption.
What's the assumption?
It assumes that every single trade is completely independent of the trade that came immediately before it.
Let me try to wrap my head around that.
Exactly.
It assumes that if my bot wins trade number 4, that event has absolutely zero statistical bearing on whether it will win or lose trade number 5.
Exactly. It treats every trade like an isolated coin flip.
But I've looked at enough trading algorithms and lived through enough market cycles to know that is often not reality at all. Strategies have streaks.
They do.
A trend-following strategy, for example, is designed to ride momentum. It might have 5 massive winning trades in a row when the market is moving smoothly in one direction, and then it might suffer 10 small losing trades in a row when the market is chopping sideways in a tight range.
You're touching on something fundamental about how markets move. That stickiness, the tendency for wins to follow wins and losses to follow losses is autocorrelation.
It's kind of like the hot hand fallacy in basketball, right?
Yeah.
A player hits 4 3-pointers in a row, and suddenly the 5th shot doesn't feel like an independent coin flip anymore. The psychology, the rhythm, the momentum, the shots feel correlated.
It is exactly like the hot hand, but with a dangerous caveat. In basketball, the hoop doesn't actively change its height while you're shooting. The market does.
Oh, that's a good point.
The market environment dictates the streak. So if your trades are sticky like that, what happens when you use the classical Bootstrap?
Well, if I'm just randomly shuffling them one by one, pulling them out of a hat, I would be artificially breaking up those streaks. I'd be taking a block of 10 consecutive losses and scattering them randomly throughout the timeline. Wouldn't that completely break the reality of how this strategy actually operates?
It would completely shatter the reality, and the consequence is severe. If you use a basic Bootstrap on highly autocorrelated trades, you are artificially dampening the volatility of the sequence. Your confidence intervals for maximum drawdown will be dangerously optimistic. You will look at your fan chart and think your risk is much lower than it actually is because you mathematically erase the consecutive losing streaks that cause deep drawdowns.
Oh man, so how do we fix it? Do we just throw the whole Bootstrap method in the garbage if we have a trend-following bot?
Not at all. The fix is a brilliant modification of the algorithm called the block Bootstrap.
Block Bootstrap. How does that change the mechanics?
Instead of putting individual trades into the hat, you partition your historical sequence of trades into chunks or blocks, let's say blocks of 10 consecutive trades. You keep trade 1 through 10 glued together as a single entity. Trade 11 through 20 are glued together.
Ah, so you preserve the streaks.
Exactly. You then tell the computer to resample the blocks with replacement, rather than the individual trades.
So smart.
It preserves the local dependencies, the natural winning and losing streaks within each block. It gives you a vastly more realistic picture of maximum drawdowns for strategies that exhibit autocorrelation while still generating those 10,000 alternate realities.
That is incredibly clever. Okay, limitation number 2 mentioned in the paper. Market non-stationarity. This is a very academic term, but it essentially means the market constantly changes its underlying behavior over time, right?
Yes. The financial markets are not static, unchanging machines. Structural, fundamental changes happen constantly. A backtest spanning 5 years might cover completely different economic universes.
Give me an example of what that looks like in the data.
Think about the market in 2017 versus the market in March of 2020. In 2017, volatility was incredibly low. The market just slowly ground upward. A bot trained in that environment expects low volatility and high liquidity. Then, the COVID-19 pandemic hits in 2020. Volatility explodes, liquidity dries up, price gaps appear overnight. The structural rules of the market change entirely.
So if I have a 5-year backtest that includes both 2017 and 2020, and I just toss all those trades into the same hat and bootstrap them, I am mixing apples and hand grenades.
Exactly. You are assuming the tranquil market conditions from 3 years ago are just as statistically likely to occur tomorrow as the chaotic conditions from yesterday.
Which is a terrible assumption. The market tomorrow is far more likely to resemble the market today than the market a decade ago. So what is the fix for a non-stationary market? How do we adapt the bootstrap?
The source material details 3 elegant solutions. The first is using a rolling window.
Okay.
Instead of bootstrapping your entire 5-year history, you restrict the bootstrap to only the last N trades, say, the last 100 trades. You generate your confidence intervals, assuming that recent history best represents the current ongoing market regime.
You essentially tell the bot, forget the distant past, only simulate based on what the market is doing right now.
Yes. The second solution is a weighted bootstrap. You put all 5 years of trades into the hat, but you give the more recent trades more mathematical gravity.
So they're more likely to be picked.
Right. When the computer makes its random draws, you adjust the probability, so it is mathematically far more likely to select a trade from last week than a trade from 3 years ago.
I really like that approach. It blends the entire history so you don't lose the long-term data, but it biases heavily toward the present reality.
And the third solution is to explicitly split your data by market regimes. You use a separate algorithm to classify your history into high volatility periods and low volatility periods. Then you bootstrap them completely separately depending on what specific environment you believe you are heading into tomorrow.
It's all about ensuring the sample you are resampling from actually represents the physical reality you expect to face.
Precisely.
Which brings us to the third and final limitation the author points out: sample size.
Now, this one is not a clever workaround. It is a strict mathematical boundary.
Right. So if I have a macroeconomic strategy that only trades once a month based on Federal Reserve announcements, and I only have a year of backtest data, that's 12 trades. Can I just run those 12 trades through the 10-line Python script, bootstrap them 10,000 times, and get a valid confidence interval?
Absolutely not. No amount of resampling magic can create statistical significance out of thin air.
Makes sense.
The bootstrap uses the data you have to estimate the true underlying distribution. If your sample size is too small, your original sample doesn't represent the true distribution at all. Bootstrapping it will just confidently give you meaningless numbers.
Garbage in, garbage out multiverses. So what is the mathematical floor? What is the magic number of trades I need before I can even begin this process?
The text confirms a classic rule of thumb derived from the central limit theorem in statistics. You need an absolute minimum of n greater than 30 trades for this to be mathematically sound.
Greater than 30.
Yes. The author reiterates that the 491 trades from the original example is an excellent, robust sample size. You can trust those bootstrap results deeply. But if you have 10, 15, or 20 trades, you simply do not have enough data to quantify your risk, period.
So we've covered an immense amount of ground here. We understand how to generate these multiverses, how to visualize the fan charts and the cliff of ruin, and we know how to correct for blind spots like streaks and regime changes.
We do.
The final piece of the puzzle is translating all this deep theory into actionable rules. If I am sitting at my trading desk with my finger hovering over the launch button, how do I synthesize all of this into a definitive yes or no?
This is where we bring everything together into a concrete application. But before we get to the specific checklist, it's worth taking a moment to quickly contrast the Monte Carlo Bootstrap with other popular validation methods traders use, just to contextualize why this specific method is so highly recommended.
Okay, let's do that. The text mentions a few alternatives. Let's start with walk-forward analysis. How does that compare to our 10 lines of code?
Walk-forward analysis is an excellent tool, but it serves a different primary purpose. It's designed to check if your strategy is overfitted, meaning your bot just memorized the historical data but has no real predictive power. Mechanically, you train the bot on a small chunk of past data, test it on a slightly newer chunk of unseen data, record the result, and then slide that whole window forward in time, repeating the process.
So it physically moves through time, simulating a live environment?
Yes. It's highly valuable,
Yeah.
but it takes minutes, sometimes hours, to compute, depending on the complexity of the bot. And crucially, it still only produces one single historical path of test results.
So it doesn't solve the single point problem.
Right. It does not give you a distribution of alternative realities or a fifth percentile worst-case scenario.
Okay, what about cross-validation?
Cross-validation, specifically K-folds, involve chopping your data into distinct segments, training on some, and testing on the others in rotation. It averages the performance metrics across these different folds.
And what's the downside there?
Well, it's very useful for tuning your parameters to make sure they are robust. But again, it is computationally heavy, takes minutes to run, and lacks the deep probabilistic insights of the Bootstrap.
And then there is the big one, which sounds very similar to our topic, Monte Carlo path generation.
It sounds similar, but conceptually it is entirely different and vastly more complex. Monte Carlo path generation doesn't shuffle your past trades. It involves using deep stochastic calculus concepts like geometric Brownian motion to generate entirely new simulated price paths for the underlying stock or asset itself.
Whoa.
It creates 1,000 fake, statistically plausible stock markets and then forces your trading bot to execute its logic on every single one of those fake markets.
That sounds computationally terrifying.
It is. It is excellent for intense institutional level stress testing, but it requires deep, complex mathematical modeling of market dynamics, and it takes minutes to hours to compute a single run.
So what is the ultimate verdict here?
The verdict from the research is clear. The Monte Carlo Bootstrap is the only method that provides a complete, mathematically sound picture of risk, including confidence intervals, fifth percentile worst-case scenarios, and explicit probabilities of ruin with a mathematical complexity level of minimal and an execution time of approximately 2 seconds.
2 seconds versus hours of stochastic calculus. It's a no-brainer.
It stands completely alone in its efficiency.
Okay, let's get to the gold, the launch checklist. The author lays out strict criteria for looking at your Bootstrap results and making the final call. Do I launch, do I tweak, or do I trash it?
Right. The framework categorizes your decision into 3 buckets. Launch, needs work, and do not launch. Let's start with the green light. You should launch your strategy into live production if and only if 4 specific conditions are met simultaneously.
Let's negotiate this. Condition 1. If my worst-case scenario still makes a tiny bit of profit, am I clear to launch?
That is condition 1. The PnL at the 5th percentile must be mathematically positive. Even when the sequence of events is incredibly unlucky, you are still generating a positive return.
Awesome.
But that is not enough on its own. You also have to look at the pain required to get that profit.
Which brings us to condition 2.
The maximum drawdown at the 5th percentile must be acceptable to your specific predefined risk appetite. If your absolute breaking point, the point where you will emotionally panic and turn the bot off, is a 20% loss, and the 5th percentile shows a 15% drawdown, you pass condition 2.
Okay, I'm profitable in the worst case, and I can stomach the worst drawdown. Condition 3.
The mathematical probability of ruin must be less than 1%. When you look at that ruin chart, you want those red paths dropping off the cliff to be an incredibly rare statistical anomaly, occurring in less than 1 out of every 100 alternate realities.
That makes a lot of sense. And the final hurdle, condition 4.
The Sharpe ratio at the 5th percentile must be strictly greater than 0.5.
Why 0.5?
This ensures that even when luck is aggressively against you, you are still being adequately compensated for the capital risk you're taking.
If you hit all 4 of those, you have a robust, battle-tested system ready for live capital. But what if the results are murky? What puts a strategy into the needs work bucket?
It requires returning to the drawing board if the 5th percentile PnL is hovering right around 0. You aren't losing money, but you are taking market risk to effectively break even in a bad scenario.
Not worth the stress.
Right. Or if the fifth percentile drawdown is massively worse than the median drawdown, that discrepancy indicates severe hidden tail risk.
Or imagine if the fan chart looks like that shotgun blast we talked about earlier. A wildly unstable spread means you need to tighten up the core logic of the bot because you were relying entirely on luck.
Exactly. You need more robust entry and exit parameters.
And finally, the red light. The do not launch criteria, the scenarios where you pull the plug entirely.
Do not launch if the fifth percentile PnL is negative. Full stop. If your realistic worst case inherently loses money, you are relying on hope, not math.
Hope is not a strategy.
Exactly. Do not launch if the probability of ruin is greater than 5%. Accepting a 1 in 20 chance of total account destruction is playing Russian roulette with your capital. And critically, do not launch if the confidence interval for your Sharpe ratio includes 0.
Because if the Sharpe hits 0, it mathematically means you are taking financial risk for absolutely 0 expected return. That is a terrible bet in any casino in the world.
This checklist is incredibly valuable because it takes all the emotion, all the ego out of the decision. The math speaks for itself.
To drive this point home, and to circle back to the hook we opened the show with, the source text reveals a truly staggering statistic from a real-world institutional application. The author references a platform called marketmaker.cc, which builds highly advanced backtest engines.
And they have integrated this exact 10-line Monte Carlo Bootstrap process directly into the core of their automated pipeline. Every single strategy that passes a standard backtest is immediately subjected to this Bootstrap test automatically.
And here's the statistic that justifies everything we've talked about today. At marketmaker.cc, approximately 30% of strategies that look amazing as a single point estimate, strategies that exhibit high returns, low drawdowns, and that quantitative traders would eagerly throw real money at, are completely filtered out and rejected by the Monte Carlo Bootstrap.
30%, nearly 1 in 3.
Without those 10 lines of code, 1 out of every 3 good strategies would have gone live, traded real capital, and likely suffered catastrophic losses, because their fifth percentile reality was actually a hidden nightmare.
It is the ultimate proof of concept. The single backtest is an illusion.
So let's bring this deep dive to a close. We have covered an incredible journey today. We started by dismantling the dangerous illusion of the single-point estimate, realizing that relying on one historical sequence is like betting your life on a single roll of the dice.
We explored Bradley Efron's 1979 breakthrough, learning how modern computers can leverage his concept of resampling with replacement to generate 10,000 completely realized alternate realities in just 2 seconds.
We learned how to read the vital signs of those multiverses, extracting the fifth percentile to stare down our realistic worst case. We visualize that risk with the spray of fan charts and the terrifying cliff edge of the ruin probability.
We acknowledged the limitations, understanding the nuanced necessity of using block bootstraps for streets and rolling windows for changing market regimes, and respecting the hard mathematical boundary of a minimum sample size.
And we walked away with a concrete, emotionless mathematical checklist to prevent us from deploying a doomed strategy.
When you look at the final return on investment of this technique, it is genuinely asymmetric. It costs a developer about 30 minutes to truly understand and implement into their pipeline. It takes 2 seconds of CPU time to run. It requires no complex external software dependencies, just basic mathematical libraries.
Incredible.
Yet, the payoff is a fundamental, structurally sound understanding of true risk that filters out 30% of hidden catastrophic failures. As the source material emphatically states, it is not optional. It is a mandatory step.
It is entirely mandatory. But we've spent this whole deep dive applying the Monte Carlo Bootstrap to algorithmic trading in Python code. But I want to leave you, the listener, with a final thought to mull over when you close this app.
Oh, I'm curious.
Think about your own career or a major life decision you recently made, maybe taking a new job, starting a business, or moving across the country. Are you judging your success based on a single point estimate? Are you assuming you made a brilliant choice just because one lucky sequence of events worked out in your favor?
That's a great point.
What would your life's fan chart look like if we resampled the variables of your decisions 10,000 times with replacement? It makes you wonder how much of our success in life is due to a brilliant, robust strategy, and how much is just one highly lucky sequence of trades.
That is a profound question. We all desperately want to believe we are the architects of the 95th percentile, but often we are just blindly writing a favorable sequence of events.
Something to think about next time you feel a little too certain about an outcome, in the market or in life. We want to warmly thank you for joining us on this deep dive. Keep questioning the data, keep looking for the alternate realities, and never settle for a single-point estimate. Until next time.